Checking the grid resolution. We can check our meshing by going to the Run tab, setting to Run in Parallel, use all the cores on the machine, in this case 4, and run for one step. We then go to the Visualize tab and look at the scalar data, C100 modes, and then we can look at the field center. This is a field that is 1 inside the shape and -1 outside. We can clip this in various ways to see how the basic shape is determined. We can see that the basic shape is fairly well computed. We can see more detail on the surface by looking under Geometries at the data surface. This is the surface after it has been remeshed to the Cartesian grid used in the electromagnetic simulation. One can inspect the surface by rotating and translating. To translate, hold down the Shift key. To rotate, hold down the Control key. To rotate, just grab and hold. At this resolution, the smallest parts of the HOM higher order mode coupler are not well resolved, but that is not important for obtaining the modes. Next, we create the current source for exciting the cavity. The current is set to match the electric field of the desired mode. To drive the accelerating modes, which have EZ on axis varying the cell, the appropriate driving current is JZ on axis, varying by cell. Since we want to excite multiple modes, we want a spatial function that covers the cells of the cavity. From the visualization and/or other knowledge, we know that the length of a cavity cell is 0.1 meters. And so we define len cav cell to be 0.1. Our goal is to excite any of the modes within a frequency range. So we choose a current distribution without any particular symmetries, but having overlap with the desired modes. We will set the current throughout the center of this cavity, starting from a beginning at cur box, what we'll call current box, cur box, to be the beginning of Z, plus that little estimate of the cell, and we'll set the end to be the same but minus. Now our goal, as I mentioned, is to set all these frequencies. So what we're going to do, we happen to know that the diameter of the waist of the cavity, let me go ahead and look at that from the plus y direction, the waist is 7 centimeters. So we define the cavity waist diameter, which we want to do, as a constant. And that constant is 7 centimeters, so 0.07 meters. We then define the radius to be half of that. And we need it square, so we'll define that as well by squaring that. Now we can define the beginning and ending of the box in the x and y directions. And we'll set that to be 0.7 times the waist radius, so that the box will be the square box, whose diagonal is square root of 2 larger, is completely inside the tube. And finally, for this part, we'll add in the end to be minus the beginning. This one should have been minus. Well, then this one is plus. We see that the center cavity is somewhere near the center And so we start by defining cav mid z up here, a constant, to be minus 0.518, which we have found to be a good value from previous work. Then we define the beginning of the cells to be the middle of the cavity, minus 3.5 times the length of a cavity cell. And we define the cells NZ to be the beginning plus 7 times the length of a cavity cell. So we now have defined the beginnings and the ends of the cells, the acceleration cells. We can now add a distributed current. And initially this box shows where the distributed current is. We're going to rename it to drive J. And initially we're going to have it start at the beginning of the cells. We'll set X to begin at the beginning of XY and to end at the end of XY. And similarly Y at the begin XY and end at end XY. And Z we will start by having at the beginning of the cells and ending at the end of the cells. And what we see is that box just barely extends outside of the tube. Because we want it smaller, we'll change this number, decreasing it a little. Before we decrease it anymore, however, we'll come back here and we'll rotate this around. And in this window, rotation requires the control key. And we can highlight that drive J. And here we see it's just barely peeking out. And here it's not peeking out at either end. And indeed, we can change this to view lines. We can look inside, and with that color, we can see that the cavity is coming, that what we have predicted for the current, or the beginning of the cavities, is indeed just at the beginning of the cavities. If it were not, we could shave cav mid Z to move it forward and backward until we had it right. Having done that, we can now go back and again decrease this slightly more. Go back to viewing solids and see now that the current square does not poke out, and therefore the current is entirely inside the tube. So at this point, we can stop and save this simulation, save our work now as the same thing, but with V3, version 3.